One such example that we can look at is at populations of species. This particular model models the growth of the gray wolf in the western Great Lakes as we started collecting data after 1978. So based on this graph right here, based on this data, we should be able to expect what the population will be X number of years after 2000 or after 1978. So for example, wonder what it would been, what it should have been back in 2014. So how do we use that to help us discover that? Well, let's use the model. 2014 is how many years after 1978 when this was begun, which is 36 years afterwards. From there, let's plug in the values. And then from there, you're going to need to use your little black box to determine what the value was in this particular model. Now, most calculators, well, pretty much every calculator has a button that's e to the x, an e to the x key. And you're going to need to use that as you're graphing these or finding values of particular ones. So I'm going to graph this 1145 on my TI graphing times e to the x button, parentheses 0.0325 times 36, on parentheses, hit enter, and I get a value of 3689.2. Well, we can't have a 0.2. Let's just leave it 3.9. So in 2014, we were expecting the population of the gray wolves in the Western Great Lakes to be 3,690 wolves on the rebound as they're being reintroduced. We can choose other years if we want. If we want to choose 2020 or 2030, we just add those values to it. So 2020 would be evaluating the function at 42. If you want to evaluate the function at 2025, we evaluate the function. 25 is how many years after 1978? It's 47 years after 1978. So we evaluate the function at that particular time. Again, evaluating a function is fairly straightforward. We need to understand that this base e does pop up a lot, and we want to be comfortable using that as a base in our exponential functions.